Okay, so we're going to be looking at chapter 13, which is about liquids and pressure. And so part one, we're going to cover pressure and liquid pressure. And let's just look at that definition of pressure first. So the idea with pressure is that pressure is force divided by area. And so in that case, it's in newtons of force divided by area, which would be in something like meters squared. And that is a new unit, which is called a Pascal. So a Pascal is a unit of pressure. Now, it's not a very large amount. A Pascal is as if you had a dollar bill sitting on a table. That amount of pressure is 1 Pascal. Okay, but here you can see this hammer, which is probably providing considerably more in terms of units of pressure. So the force, of course, would be the force of the hammer pushing on this window glass. The area is the area that is the part of the hammer that's in contact with the window glass. Okay, so anyway, so force divided by area. All right, so let's discuss some of the things that could go on here. What if the area is larger? What if the area is smaller? Um, well, um, that does make a big difference. And also, where do you get the force from? Force could be provided by air pressure. It could be provided by someone pushing something, a hammer. It can also be provided by weight. So often something might be sitting on a table. It's applying pressure. So it is the weight of the object. So sometimes this formula, you might want to think of it as mg, weight, divided by area. Now, the area again matters. If the area is large, then that is a lower pressure. And so this is one reason that you often distribute pressure. So if you're on ice and the ice starts to crack or something, it's good to get down maybe on your hands and knees, or if you're trying to rescue someone, they send out a ladder to distribute your weight over the ice. But a small area gives a higher pressure. And so women in high heels, or anybody in high heels, have often found that you sink in the mud, so your high heel goes into the mud, whereas someone with a flat sole can walk easily across. Same thing for a knife blade here. You have a sharp knife. It easily can apply the pressure that can cut the skin of vegetables. Vegetables have a tough skin. They require a lot of pressure to push through them. So when you have a smaller area, so if the area was half as much, you could have twice as much pressure for the same force. And so a sharp knife will cut vegetables more easily. And also when you get a shot, they can use a big needle, which has a large point, or a small needle. The butterfly needles are the really tiny ones. And most people prefer those because the nurse doesn't have to go, as she pushes it in. She doesn't have to use a lot of force because the area is so small, right? You don't want your nurse doing that. Okay, let's look at some examples then. Here are two blocks. Let's label them A and B. And the question is, which do they have the same pressure on the table? And the answer would be no. They have the same mass. They have the same volume. But the area they're sitting on is not the same. This block is sitting on an area like this. Block B is sitting on a smaller area. So which one is applying more pressure? The one with the smaller area, right? So let's go prove that. Okay, so pressure is force divided by area. And let's do block A first. So again, because what's pushing downward is the weight of the block, then we're going to change this to mg divided by the area. Okay, so pressure is mg divided by the area. We've got a mass of 15 kilograms. So that is not the force, of course. That is just kilograms. Mass So to make it into a weight or force, we need to multiply by g, 10 meters per second squared. And we're going to divide by the area. Now, for block A, the area is going to be 5 by 20, right? That's the size of the area for A. Now that's 5 centimeters by 20 centimeters. So we might want to change that to meters so that we can come out in pascals. So 5 centimeters is 0.05 meters, and 20 centimeters is 0.2 meters. So we're going to get 0.05 times 0.2. And you want to do it now. You don't want to save it and transfer it later because that's going to be messy trying to do the conversion later. Okay, so now we should have over meters, and that will be squared, right? Okay, so doing the math, what are we going to get? We're going to get, well, on top we've got 15 times 10, and that's going to be 150. On the bottom we've got 0.05 times 0.2, and that is 0.01. So we're going to come up with, that's going to be pretty large, right? So 150 divided by 0.01 is going to equal 15,000 pascals, right? Newtons per meter squared. Now, one thing is that because pascals are so tiny, we often have numbers that are larger than that. So what you do is we make them kilopascals. So this one is going to come out to be 15 kilopascals, right? Thousands of pascals. So kPAs is often a unit used for pressure. Okay, now what about block B? Well, for block B, the area is going to be 5 by 5, right? Instead of 5 by 20. So, so how would that change our problem? Well, what that's going to do, of course, is take out the 20 here. So the same force, but the area has changed quite a bit. So 0.05 times 0.05 is going to be 0.0025. And so what's that going to do to the pressure? Well, it should be 4 times greater. Let's see. All right, so yes, 60,000. So it's going to come out to be 60 kilopascals, right? 4 times greater because the area is actually 1/4 as much because you could have fitted in 4 of the 5 by 5 areas in that 5 by 20 space. Okay, drawing's not to scale. Anyway, so yes, so it should be 4 times greater force, 4 times greater pressure because we have 1/4 the area. Now, when you, if you've ever lain on a bed of nails, which, by the way, I own beds of nails that students made for me. The college uses them, so here's them being used at the college by physics professors. Anyway, so we put our professors on top of the beds of nails, and then we put a concrete block on top, and then we smash it with a sledgehammer. So the brave professors do this for fun. Anyway, so yeah, so I'm laying on the beds of nails, and you know, it's totally survivable. Why is this guy laughing? I'm sure he's laughing. He's got a whole other person standing on top of him, so maybe he's going ow a little bit. But that is not blood. I don't know what it is, but it's not blood. Anyway, but why can you do that with nails? Well, one nail would really hurt if you've ever stepped on a nail, but 1,000 nails, you don't hurt as much. Because you have 1,000 times more area, so actually the pressure that's required to break your skin, there's less than is required for that. Okay, so it's 1,000th the pressure one nail would have. So 1,000 times more area, 1/1,000th the pressure. So yes, so when Dr. Fazzini gets up, he will not actually be bleeding. All right, and that's Dr. Carter. Oh, and there they are again. There's Dr. Fazzini now in the abusive role, and we've got Dr. P is underneath there, Pulaski. Okay, so anyway, so yes, this is something they use my boards a lot. Okay, so yes, so sometimes I allow the students to lie on the beds of nails, usually for some extra credit. Anyway, so for liquid pressure, it has to do with the water molecules that are pushing down on you. And we're going to discuss air pressure in a next chapter. So liquid pressure is as you go deeper and deeper in the water, then the water molecules are pushing on you with greater and greater force. You've got all the water molecules above you, gravity's pulling on them, and you're in the way. So they push on you. Okay, now liquid pressure depends on depth. So as an object goes down deeper in the water, then the pressure becomes greater. Now, for depth, we use the letter H, which we use for height. Okay, so here it's depth. That's the same thing. It's a certain distance. And then there are these letters here. Now, if you remember rho is the letter for density, symbol for density. And of course, then we've got G, because we're on the planet Earth. If this was a different planet, you would have to have a different G. Okay, so pressure in a liquid is rho GH. That's the formula. Okay, and we'll do an example in a minute. Okay, now, of course, pressure acts equally in all directions, but this means that if you have a boat in the water, then the water pressure pushes the boat upwards. But if you're swimming under the water, then your ears are going to hurt no matter what direction you are under the water if you get too deep because of that water pressure, right? Okay, now here is someone snorkeling under the water, and he got photobombed by this fish there, parrotfish. And so anyway, snorkeling is a lot of fun. If you ever get a chance, go snorkel, go to a reef while they're still around, snorkel. Okay, it's wonderful. Anyway, so this snorkeler went down to 2 meters. So he's about 6 feet under the water. So he dove down. What is the liquid pressure at that depth? Okay, so pressure is rho GH, and rho is the density of water. And when you're doing these problems in this chapter, you're going to want to use the kilograms per meter cubed amount for the water. So water, which is 1 gram per centimeter cubed, but remember it's 1,000 kilograms per meter cubed. So that's going to be the density that we need. So the density of water is 1,000 kilograms per meter cubed. Now, is that the one we're going to use though? This is not fresh water. This is salt water. So when it's salt water, you actually want to use a slightly higher value. So for salt water, it's 1,025 kilograms per meter cubed. So I'm going to use that one because this is salt water. A little bit more dense. Okay, so let's put that in here. So we're going to have the density of the water and the depth under the water. So we've got 1025 kilograms per meter cubed. We've got G, which is, we're going to use 10 meters per second squared. And we've got the depth, which is 2 meters. So you see why you want to use meters or kilograms per meter cubed, because you're going to use meters in this problem. All right, and for G. Okay, so what do we get now? Well, we're going to get 20500. All right, 20,500, and this will come out in pascals also, okay, or newtons per meter squared. And which it will, okay, if you play around with it, and which of course means that it's 20.5 kilopascals. Now, many animals, as they go very deep in the water, they experience a lot of pressure. And they have found that sometimes seals and whales that are very deep divers can actually crack their ribs. The deepest place in the ocean is the Challenger Deep, part of the Marianas Trench. And that is over by Japan, Guam. And so it is 10,000, almost 11,000 meters deep, which is 6.8 miles. And there have only been a few people who have gone down to that depth. One of those was James Cameron, who was a director of some famous movies like Titanic. And he had himself a ship built that he was lowered down to the bottom of the Marianas Trench. Now that trench is so deep that you can fit Mount Everest into the trench and there would still be room left over. So anyway, it was so deep that the pressure at that point was incredible. We aren't going to go ahead and calculate it, but you could, right? You've got the depth. And so the depth in meters is 10,994. Go ahead and use the pressure for salt water. All right, so you can know that the depth or height is 10,994 meters. And you could go ahead and use the formula, pressure, rho GH. Okay, so same formula, just a lot deeper than our diver went. And when you get down to the bottom, well, that's where a picture of the bottom. So they had some submersibles that went along with him to take pictures. Now, was he the first person to go down there? No. The first people to go down there, that was actually in the 1950s. The Navy decided they wanted to know what was down at those depths. And they sent two very brave naval officers down in a bathysphere, a globe sort of thing. It had a small window which started to crack as they got partway down. And so they got down to the bottom, but when they hit bottom, it poofed up all this sea soil there. And so the sediment, and they didn't really get to see much. But anyway, but they did go down and survive in the 1950s, which is amazing. Okay, now in your home, you sometimes have to worry about water pressure. Sometimes the water pressure will be low because the city is doing some repair work or something on the water lines. So where do you get water pressure from? Now, if you live near mountains, sometimes the water pressure is provided by the fact that the water is coming from a higher place. So the Romans carried water in aqueducts from the mountains to the city of Rome. Now, the city of Rome had rivers running through it, the Tiber River, but they didn't want to drink that water because the Tiber River was basically the toilet of Rome also. So they brought in fresh water from out of town, and it even had to cross rivers to get to Rome. Once it got there, because the aqueduct was higher than the city, then it provided pressure to make all the fountains. So as it would come in to the city, it was higher, and so then fountains could shoot upwards because of the pressure that it was providing. So pressure is provided by the height, okay? The water is. So what we do in our cities usually, because it's flat around here, is we have water towers. So they've got water in them that's pumped up continually. And so then it's allowed to release through pressure, so it goes down, and then it goes through pipes to your house. All right, so let's say you live in a building and it's 3 stories tall. And so everybody has a bathtub and a shower. Who is going to get the best water pressure? Well, the depth actually depends on the difference in the height. Okay, so the difference in the height here, let me change to a color that's not blue. All right, so the difference in the height is what gives you the water pressure. Okay, so anyway, so who's going to get the best pressure? The one with the greatest change in the height. So the pressure is going to be rho g delta H, and that's going to provide the pressure. So the person on the top floor may not have great pressure, the second floor will have better, and the third floor will have the best of all. Oh, did I mean that? Third floor down, first floor will have the best water pressure. How do buildings get pressure when they're tall buildings, taller than the water tower? Well, most of the time we don't have those around here, but some hotels get built taller. And of course, in Chicago, they put the water towers up on top. So you'll see in Chicago the old-fashioned water towers, although the city is trying to get rid of those because those have been around for like 100 years. They're very dangerous. So those are on top of the buildings. They're very dangerous. A few years ago, one started to come down because they had rusted away, the supports. And it did fall down, and the building had to be, everybody had to be taken out, and nobody knew what was going to happen. Fortunately, nobody was injured. But it was very exciting, and so the city said, okay, enough is enough. Anyway, so nowadays they're replacing them. And so you'll see on top of buildings sometimes, high buildings, like there's one called Water Tower Place, which looks like it has a birthday cake on top. Used to have really obnoxious lights. They toned those down a bit. It's not too far from the Hancock, well, not the Hancock, the Sears Tower, as you drive into Chicago. So anyways, they're disguising their water towers there. Okay, so anyway, animals can have difficulty with this too if they have high neck, so like a giraffe. Think about the pressure difference between when their head is down and when their head is up, because that difference in height, giraffes can be like 16 feet high, makes a huge difference in the pressure of their blood. And so giraffes have all these fancy valves and stuff in their neck so that water can't just, or blood can't just flow easily. They also have a tremendously large heart to pump that blood up to those levels. So pressure depends on depth. And so what happens is when you have connected pipes, then the water level will be the same for all of them. Okay, these water levels, the pipes here may have different shapes, but the water level is the same. And because if you had higher pressure on ones, then it would push water into the others, and then they would be higher, and so they would push back. So what happens is all the water level comes to the same height. So here we've got a small deep pond and a large shallow lake. This is one of your homework questions. Which one has greater pressure? The depth is what matters, right? So depth matters. So yeah, the 6-meter one is more likely. And also there's a question you have about dams. Why do dams have are thicker at the base? I mean, there are a couple of reasons for building them, but for one thing is pressure gets greater as you go down. So the water pressure gets greater as you go down. Okay, so it's less as you go up. So you need a thicker dam wall down below to hold back that water. Okay, so pressure does act perpendicular to all surfaces. And again, the greater the depth, the greater the pressure. So you end up having a water, when you poke holes in like a styrofoam cup, it'll come out faster from the bottom hole because that's where there's greater pressure, which makes greater force. Okay, so greater pressure is greater speed because force is pressure times area. And so you've got a greater force as you go deeper. So from the top hole to the bottom hole, that's 1, 2, 3 times as deep. So whatever force we have here, we would expect 3 times as much force down below. So pressure is force divided by area. So force is pressure times area. And if you have net force, that's going to be the net pressure times the area. Now, usually you don't have windows in submarines. And the reason is that the submarine is so deep that the water pressure is enough to break a window. And so when you think about a submarine, what you've got is, let's look at a window here. Let's pretend that there's a window in this submarine. And the idea is inside the submarine, there's usually some pressure maintained, but let's say they just have that equal to air pressure, regular air pressure, which is like 1,000 pascals. But if you're 200 meters deep, what's the water pressure? Well, we can figure that out. And again, probably they're in salt water. So rho GH, it's 200 meters. And you would get 205,000. All right, so we would get a lot of water pressure. We would have 2 million pascals of pressure compared to 1,000 pascals on the inside. So you can see how you would have a huge difference of pressure. And so we could figure out the net force by taking the net pressure and multiplying by the area. Okay, so if we're looking for the net force, which here it's 2 million times divided by 1,000, so really basically it's still 2 million. Okay, so we haven't taken much off. It would be 2 million, 2049. Okay, so anyway, so it's still about 2.05 million. And we're multiplying by an area which is 0.04 meters squared. I'm going to make that 4 times 10 to the minus 2. Okay, and so what I'm going to get is 8.1 times 10 to the 4th. And that will come out to newtons of force. So it's a huge amount of force. And that's why we don't have windows in submarines, usually. Okay, so having a window, it has to be double thickness, triple thickness. So James Cameron had a window, those naval officers had a window, and that was much deeper than this 200 meters deep. But those windows, as I said, for the naval officers started to crack. I think Cameron started to crack too. Okay, so very, very dangerous. Okay, so that's the end of this part. We're going to continue with buoyancy and the buoyancy force. Okay, so stop.